Hey guys, welcome back to Explore Electronics. Let us understand MOSFETs in this video and also see different types of MOSFETs and the working of those. We have nMOS transistor, we have pMOS transistor, and further we can categorize them as enhancement mode transistor and depletion mode transistor. So basically MOSFET in the sense metal oxide semiconductor field effect transistor, which will be having metal under that oxide under that semiconductor regions, and it will work on the principle of field effect. And if you see the physical structure, it will be having a gate region, source region, drain region, which is source and drain created in a substrate region. And if you look at the physical structure in detail, the P region is a substrate over here. In that we will be creating two N regions, we call it as nMOS transistor. If the substrate is of N type and we are creating two P regions inside, we call it as pMOS transistor. Let us understand more about this and how actually they work. In that, the very first thing is nMOS enhancement transistor. In the nMOS enhancement transistor, we need to understand the physical structure first. Initially it will be a pure silicon, then the P impurities will be added and make it as P-type silicon. And once it is become P-type, we need to create two N regions by adding N impurities only for this particular region. And after that, there will be an SiO2 deposition, that is insulator, and that will be act as an insulation between the gate as well as the substrate. And gate region is polysilicon, which is placed above SiO2. And now we will be getting source, gate and drain and a substrate connections over here. So this is enhancement mode transistor, where there will be no connection between the source and drain for the current flow. We need to create the channel between source and drain by applying the extra voltage from the gate. Now, if you look this further, there will be two back-to-back diodes formed inside because of the N and P regions. This is N region, this is also N region, this is P region. So here you can easily see there is a PN junction over here, and here also there is a PN junction. So internally, the transistor structure will be containing two back-to-back diodes. So that will not allow the current to flow through device inside the device. So by applying the voltage only, we can create the channel between source and drain and we can expect some current to flow. Now if you look at the symbol of the enhancement mode transistor, it will be representing the terminals. This is gate terminal and this is drain terminal, this is source terminal, and this indicates the gate, and from here it will be a substrate. But you can see the clear-cut difference between these two, that is an insulator. This is the symbol of nMOS enhancement type transistor. That will also be represented in different manner like this. This is a simple symbol. Here this symbol indicates if the channel is created in between source and drain over here, and this becomes a N-type channel, and here is the P substrate, obviously a diode will be created over here between these two like this. So diode direction will be towards the channel. So this arrow mark indicating that diode. And here is one more symbol that will be indicating the direction of current flow. So here this end is source, this end is drain, and this is gate. And there is a arrow mark indicating at the source. This arrow indicating there is a current flow from drain to source in this direction. This is about the symbol of nMOS enhancement mode transistor. The thing we need to remember here is, once we say enhancement mode transistor, there is no channel exists between source and drain at the starting. Channel need to be created by applying the voltage from the gate. That is about enhancement mode transistor, physical structure, and how actually the channel will be created. Now comes the working of nMOS enhancement mode transistor. We need to understand how actually it works. So basically, we need to understand how the voltages are going to be provided from the gate and drain, and how the channel is going to be created, and how the current flow is. So to start with, we can see this is the arrangement we can make to apply the voltages. So we have a substrate here, it is of P-type, that will be always connected to source and it is grounded. You can see this. And then we have two voltages here. One voltage is between VGS, that is in between gate and source. The other voltage we are going to apply is VDS, that is between drain and source. Since the source is already grounded with respect to substrate, this can be a negative terminal now or a ground terminal. Whatever the voltage we are going to apply from gate will be with respect to source. So positive voltage will be applied to gate. Similarly, there is another power supply you can see here. Positive terminal connected to drain and the negative terminal common point connected to source. So VGS will be a gate voltage we can directly say, and VDS is a drain voltage we can say. So now we need to understand what happens when we apply the voltage. If we apply the voltage from gate terminal, if the gate voltage VGS is greater than the threshold point, threshold voltage VT is a level of voltage from the gate to create a channel between source and drain. Means, in other words, we can say a minimum gate voltage required to make the channel created between source and drain in a nMOS enhancement transistor, that is VT. Generally, in a silicon type transistor, this VT will be of 0.7 volts to 1 volts. So this is the threshold voltage. So we need to apply the voltage from gate more than that to create a channel between source and drain. And what happens when there is no voltage from the gate? No current flows from source to drain because of there is no channel at all, right? There are two reverse biased junctions, means that is PN junctions, connecting back to back in between source to substrate as well as substrate to drain. Once we start applying the voltage positively from the gate, what happens? Here some positive voltage we applied means all the positive charges accumulate on the gate. Gate becomes more positively charged. It creates an electric field across the substrate now. This creates an electric field over here. Because of that, it will attract the electrons which is negatively charged towards the gate, and it will repel the positive charges, that is holes, towards the substrate. So generally what happens here means when we start applying the voltage from the gate, electrons are attracted towards the gate and holes are attracted towards the substrate. That forms an N region over here, which is of electron region. Previously, if you see, this is a substrate where the substrate will be having majority of holes. They are positively charged. P will be having majority of holes and N region will be having majority of electrons. Now the electron region is created over here and this will be called as an inversion layer. So that inversion layer is the name comes because previously it was P region, now we inverted that into N region. So because of attraction of electrons towards the gate, we have created the electron region over there, we call it as inversion layer, right? You can see over here, this is gate, here also this is VGS when it is equal to VT. This is when we are increasing the VT. What happens when we increase the gate voltage more than VT means this channel becomes stronger. This channel becomes stronger means more channel depth we are going to get, and you can see over here compared to this channel depth is less here in the first diagram where VGS is nearly equal to VT, and when it is VGS is more than VT, the channel depth increases. We will be getting the strong channel to create the connection between source and drain. Further increase in the VGS making the channel stronger, as well as if we start applying the voltage from drain, the current flow started between source and drain. That we need to understand in the next here. So if we clearly understand the working of the transistor, which is nMOS enhancement type, when VGS is equal to 0 and VDS is equal to 0, there is no channel exist. And when we start applying VGS, that is more than VT, and we assume that VDS is equal to 0, we applied only VGS that is greater than VT. That is sufficient to create the channel between source and drain, but there is no current flow between source and drain still, right? Why? Because when we are expecting a current means that is from drain to source here, because of the voltage we are applying from drain is positive and source is negative. So the current flow will be from drain to source. Since VDS is 0, there is no current flow, but because of VGS we applied already, there is a channel created. This region will be called as cutoff region. Even this will be a cutoff region, but even if we apply gate voltage, channel is created and VDS is 0, there is no current flow, we call it as cutoff region of operation. So now in the next thing what we need to understand is, by keeping VGS more than VT, by creating a channel, what happens when we apply VDS further. So that is the next thing. When VGS is greater than VT and VDS is less than VGS minus VT level. So here what happens, it is assuming that VDS we start applying positive now from the drain. So because of this, it will start the current to flow through from drain to source. Current will be started. And if you look at the physical structure of the transistor here, this region channel is thinner and towards source it is normal. This is the channel depth, it is normal towards the source, and towards drain the channel becomes thinner. Before understanding that, we need to know the current flow. So when VDS is positive, the electrons will start moving from source to drain. Source to drain the electrons move will be, and the current flow will be in the opposite direction we will consider, right? So current I will be from IDS, correct? And as VDS increases, if we increase VDS further, obviously IDS also increases. This happens until this VDS is less than VGS minus VT level. This increment happens only until this VDS what we are going to apply will be less than VGS minus VT level. Now we need to understand about the channel, what is happening here. If you see how much we are going to apply the voltage from the gate, that much deeper the channel will be created. This is because of at the end of gate to source, gate voltage is positive and the source voltage is negative. That's why here sufficient number of electrons are going to be created. If you see at the drain terminal, if you start applying voltage from drain as positive, gate also will be having a positive voltage. Because of that reason, here the voltage drops and there are less electrons available at the drain end. That is why if we keep VDS less than VGS minus VT, as we increase VDS, current also increases, right? But if we increase this VDS further, the channel becomes thinner towards the drain and finally it ceases. That is the next regions of operation we need to see. But here until it is in this condition, it will be called as a linear region. Current will increase linearly as this is current ID. If you take this as VDS, as VDS increases, current also increases. That is linear increase in the current, and it will be also called as a resistive region. Now the next thing is when this VDS is equal to VGS minus VT. Till now we have seen VDS is less than this condition. Now this VDS is equal to VGS minus VT. What happens? Here this is also positive, this is also positive, and here the voltage drop occurs. Because of that, there is no channel exist at the drain end. Until it is less, there is a channel existed. Once VDS crosses that limit and we increase further, the channel pinch off. We call it as channel pinch off. This is the place where we call it as channel is pinch off. There is no channel exist at the drain end. At this time what happens? The current dependent on VDS will be less. Means there is no dependency of current on VDS. Even if we increase VDS further, current will not increase. Current becomes constant. There is a constant current flow. So in the linear region what we have seen, as VDS increases, current IDS also increases. But in the saturation region, VDS increases further, current will not be increased, current is constant. Current becomes saturated, we say. That's why it is called as saturation region. So in the saturation region, current will be constant and the device will be act as a constant current source. We call it as current source, and also we are going to use this in amplifier devices, and we are going to use this region of operation in switch devices. When we are going to use it as a switch, we will be use it in the linear region. When we are use it in the amplifier region, as an amplifier, we will be putting the transistor in a saturation region. That is what the enhancement mode operation is. If you look at the transfer characteristics, that is current versus voltage, you can see here. So this is VDS, this is ID. So we start applying from 0. When VDS is equal to 0, there is no current. As VDS increases, you can see current also increasing, right? For any particular value of VGS, this might be the curve. Suppose if VGS also increases, current also increases. If VGS increases further, current also increases. Up to some level, you can see up to here the current is increasing, and after it reaches VGS minus VT point, current becomes constant, and we call it as saturation region. This region of operation will be called as saturation region, and this region will be called as linear region. And when there is no VDS and only VGS is applied, current will be zero. We call it as cutoff region. Once we start applying VDS, then only current will started to flow. This is about enhancement mode transistor. Then comes the depletion mode transistor. What is the difference between enhancement and depletion mode transistor? We need to see here. This is also created in a P substrate by creating two N regions, and at the time of creating N regions only, the channel is created here. You can see the difference clearly between the enhancement and depletion. Here the channel is created at the time of creating the active regions, source and drain itself. Above that there will be a silicon dioxide, and polysilicon will be act as gate. Now when the gate voltage is 0, there will be a channel exist. When the gate voltage VGS, even if it is less than VT, that is 0, the channel will be present. That is depletion mode transistor. The major thing we need to understand here is this channel which is already created. We can apply the voltage from drain, and we can expect a current without applying any voltage from gate here. That is what depletion transistor is. And here also there will be a back-to-back diode connection. And if you look at the structure and a symbol now, this symbol will be similar to enhancement mode transistor, but the difference is that in between source and drain regions there is a thick indication over here. This thick indication indicates the channel is already there. The channel is created at the time of manufacturing itself, right? So this thick line we need to put to indicate this as a depletion type transistor. So here the takeaway is that channel exists between source and drain already. Channel can be removed, channel can be seized by applying a negative voltage from gate. So in the enhancement mode transistor, what we did, we need to apply VGS positive to create the channel. When VGS is equal to 0, there is no channel exist. Now in the depletion mode transistor, here only channel is created. By applying VGS is equal to negative, right, negative voltage, we can seize the channel or we can remove the channel. That is about nMOS depletion mode transistor. Now comes pMOS enhancement transistor. As we know, pMOS transistor will be having a N substrate. Inside a N substrate will be creating two P regions. They act as source and drain. Above the substrate will be having SiO2 layer. Above that will be having gate layer. And the four terminals are source, gate, drain and substrate. Here the substrate is of N type and the two active regions are P type. If we create a channel between the source as well as drain, this will also be a P type channel. That's why we call it as P channel device, right? And if you look at the structure and a symbol will look like similarly as a MOSFET, enhancement type N transistor, but we will be having a bubble here. This bubble indicates we need to apply the negative voltage from gate to make the channel created, and also we need to apply the voltage negatively to make the transistor on. That is the meaning here by putting a bubble over here, right? And the symbols you can see similarly as enhancement mode N transistor what we have seen here, the different symbols are there. This bubble indicates P type, and also there is an arrow mark over here which is pointing downwards. It means the channel will be of P type and PN junction will be in this direction, right? That's why here the arrow mark is downwards. And if you take this as source and drain, the current will flow from source to drain here. It is not IDS, it is ISD. That is about a pMOS enhancement type transistor. Here also there is a depletion region. Why? Because of the PN junction formed over here. If you see any PN junction diode, this is P region, this is N region, this is the junction where the positive negative ions will be combined over here and creating a depletion region. Because of that, we need to provide a minimum threshold or cut-in voltage from the P region to cross this barrier, right? That is the depletion region which will be created here also. And coming to the working of this, channel will be created by applying negative voltage from the gate, and current flow will be because of the holes movement from source and drain. Here, because of this is P, here also positive ions are there, positive free charges are there, and the region created over here will be also of P type. Because of holes movement, there will be a current flow here. In the N transistor, because of electrons movement, the current flow will be. Electrons will move from source to drain, so we call it as the conventional current will be from drain to source. Here holes will be moving from source to drain, and also the current will flow from source to drain, right? That is about nMOS transistor and pMOS transistor. There is no concept of pMOS depletion type, so only pMOS enhancement type is available for us to use. This is about the working of nMOS enhancement mode transistor and pMOS transistor. In the next video, we will be seeing what is threshold voltage, how we can control that, what is body effect that will be affecting the threshold voltage of the device, and how we can derive the expressions for current, that is IDS, in cutoff region and also in linear region and saturation region. That is very much interesting. Let us see the derivation in the next video. Thank you.